Next up in our video series is a discussion of resistors in parallel, and we'll see exactly what that means as we progress. Let's go back to where we started yesterday. Let's think about a 10 volt battery across a 2 ohm resistor. Now I've added a little something today. This circle with an A in it represents an ammeter. An ammeter, as the name implies, measures the amperage or the current that's flowing through it. So any current that flows through this 2 ohm resistor will flow through this ammeter, and it can tell us what that current will be. Well, what will that current be? What would that ammeter read in this situation? Whoa, magic. This time I paused and didn't ask you to. It's reading 5 amperes. Now, I didn't use proper significant figures because I am trying to work with the little space I have. That should be 5.0 amperes, of course. But 5 amps are running through that resistor. 5 amps are running all the way around this circuit. Now, let's do a little bit more magic. Whoa, how'd that happen? So now we have 3 ohms and an ammeter arranged in the circuit as well. And you'll notice current can go from the 10 volt battery through the 2 ohm path, and it can also go through the 3 ohm path. Interesting. We've got 2 different paths that the current can take. Current that goes through the 2 ohm path doesn't have to go through the 3 ohm path, and in fact it can't and it won't. It's going to just travel along there. Meanwhile, current that goes through the 3 ohm path doesn't have to go through the 2 ohm path. It can't and it won't. It's going to go this way, all the way around the outside loop of this circle, of this circuit. So if we were to read the ammeter shown here, how many amps do you think are flowing through this one? I'm going to give you a second to think about that one. And now you're back, I hope, with an idea of how much current flows through a 3 ohm resistor. Well, what we really want to know is what's the potential difference across that resistor? And to ask that question, and to answer that question, let's consider the difference in potential between, let's say, this point marked in red and that point marked in red. To answer that question, what's the resistance from, let's say, the point that I'm calling A and the point that I'm calling B? Those 2 locations both have potential values, but there's no resistance between them, so they must be the same potential value. After all, delta V equals IR. And if R equals 0, then delta V also equals 0. All those places have the same potential. Meanwhile, on the other side of the circuit, every place in green also has the same potential. Now, here's a little rule that we learn when we talk about circuits in this class. We learn that there is no resistance in an ammeter. Ammeters are just like plain resistanceless wires, so we're going to treat them as such. So now, what is the potential difference if I put a voltmeter across the 3 ohm resistor? What's that going to say? I'll give you a moment to think about it. And now that you've unpaused, I hope you realize 10 volts across a 3 ohm resistor has no choice but to result in 3 1/3 amps. I'm going to call it 3.3 amps for the sake of brevity, and I can only fit so much in there, and we only have 2 significant figures in our value, but we can think of it as 3 1/3 amps. That'll come in handy in a moment. These 2 paths are called parallel paths, and these resistors then are arranged in parallel. Oops, I just added another ammeter. What is that ammeter going to say? Remembering that all the current that flows through here must go that way, and all the current that flows through there must also go through that same ammeter. So what's the reading on that ammeter going to be? Oh, there it is. It's 8.3 amperes. If you thought 8.3 amperes were what's flowing through this entire circuit, you'd be absolutely right. So now ask ourselves, how much resistance is really resisting the flow around this circuit through the 10 volt resistor? I'm sorry, from the 10 volt battery. And to answer that question, we just use delta V equals IR. So how much resistance? Well, R must be delta V over I. That's 10 volts divided by, let's call it 8 1/3 amps. 10 volts divided by 8 1/3. Why, that sounds like 1.2 ohms. 1.2 ohms is the total resistance going around this circuit. Now this may seem strange. We added a 3 ohm resistor to a 2 ohm resistor and got less than 2 ohms. In our next segment, we're going to talk about how that actually works. And it actually makes a lot more sense than it might sound at first.